So as I mentioned, this is the Rust Book Club. We're getting very close to the end of the book now. So we've gone all the way through chapters 1 through 18. We've taken a little bit of a longer break since chapters 17 and 18, partially to let those ideas digest a little bit because there was quite a lot of meat to those subjects, but also because chapter 19, Advanced Features in Rust, was also quite a big chapter as well. Ciara is going to start us off with chapter 19. So yeah, take it away, Ciara.
Okay, so yeah, I'm going to be covering chapter 19. I hope some folks have had a chance to go through it, but if not, I'll do my best to fill you in. We're going to cover Unsafe Rust, Advanced Traits, Advanced Types, and Advanced Functions and Enclosures. I'm actually not going to get to macros, I don't think, because there is a lot in it, and I don't think we'll have time to do it justice. We can kind of discuss it informally, but I probably won't go into a great deal of detail. Also, because Chris is going to be doing hopefully a session on it very soon, in which he's going to do a deep dive into macros, because macros are pretty awesome in Rust, especially if you're if you're used to being fearful of the word macro. So, what is Unsafe Rust? Well, Unsafe Rust means, trust me, I know what I'm doing. I'm a software developer. It gives you access to the programming features which don't give you the usual safety guarantees that we kind of get used to in Rust. And it's because the compiler can't provide those safety guarantees. The ones it can provide, it will, but there's some things that if you want to do it, you're just going to have to be careful. The regular borrow checker rules all still apply, so you can still rely on all the normal things you're used to. But if you do any of these things, which you could only do in an unsafe block, then the correctness of your code you'll have to determine, which includes dereferencing a raw pointer, calling any other unsafe function, accessing or modifying a mutable static variable, which is the equivalent of the dreaded global in other languages, implementing an unsafe trait, or accessing fields of unions, all of which we'll come on to. It's the dereferencing of the raw pointers that's the problem. Creating raw pointers is fine, there's nothing that can go wrong there. But if you dereference a raw pointer, there is an assumption that that pointer is correct. They're special because you can ignore reference borrowing rules, so you can have both immutable and mutable pointers or multiple mutable pointers to the same location. And this is something that you can't have with the usual borrow checker rules with references. It's really locked down so that you know that you've only got, if you've got a mutable reference, you're the only one with a reference to it. If you've got an immutable reference, you know that you can read from it as much as you like because no one has a mutable reference at the same time. Raw pointers also aren't guaranteed to point at valid memory. You can create a raw pointer pointing wherever you like on your machine, and you can make your application go boom. And they're allowed to be null as well. And if you dereference a null pointer, anyone who's worked with C++ or C will know bad things happen. Not the worst things, but certainly some bad things. And they don't implement any automatic cleanup, which means you can get things like memory leaks if you choose to allocate and then manage that memory yourself. Your raw pointers, if you lose your raw pointer to your memory, it's not going to get cleared up for you. So why would you ever want to use these? Well, there are performance benefits. So you don't have to take the hit for any of the overhead of managing your references or anything like that. It's just a completely dumb, simple raw pointer. This means as well you can interface with other languages that have those raw pointer types and also interface with hardware. So how do you actually use them? Well, you can cast immutable and mutable references into their corresponding raw pointer types. So that's what this code is doing here. So you're taking your reference to your number, and then you're taking it as a const raw pointer to 32. And that means that here, when you dereference it, this bit needs to be in an unsafe block, because although we know that this raw pointer is totally valid, it's just a pointer to this number here. There's no way that the compiler can know that because we could have put whatever we wanted in here. So as a result, that dereference has to be done in an unsafe block. And if you want to see what creating an invalid one looks like, you can just say, okay, here's my address, cast it to my pointer type, and then dereference it, and it'll go boom. So you can see why it's useful to have it in an unsafe block, because when you get exceptions like this, you know where to look. Most of your code is safe. You're not going to get it in it. So you only have to kind of check your unsafe blocks. If you call another unsafe function and it's been marked unsafe, then that means you can only call it from an unsafe block. And the reason you would do that is to indicate that your calling code needs to be careful that it's not violating any preconditions and that everything works. So it's kind of putting the onus on the calling code to check that the code is safe. That's why you might mark a function as unsafe. So it tells the compiler that if we say we're going to call this unsafe function, then we have to put it in an unsafe block, which tells the compiler that we know how to use this function properly. We've looked at the doc for it, and we're fulfilling the contract of this function. So nothing bad should happen in theory. So to show you what that looks like, here we've got a function which doesn't even do anything unsafe, but we've marked it as unsafe. And by doing that, we have to call it from an unsafe block. Now, our function that we're calling that from within is not marked unsafe, even though it's got an unsafe block in, which means it's saying, look, there's no preconditions, there's no postconditions or anything. Anyone can call this code and it will work. Whereas this function, even though it's not doing anything unsafe, is saying, oh, be careful here. This should only be done with caution. And a lot of the standard library functions will have unsafe code, but when you're calling it, you'll be in a situation like this where the function you end up calling is not unsafe, so you can just call it normally. But inside that implementation, there will be an unsafe block. Example they give in the Rust book is split at mutable, which means you get two mutable slices in a tuple. And so the unsafe block is conceptually saying, I promise to return two slices that won't overlap. And that way, you know that they act totally independently. You can get two references and they can both work independently. What we want to write is something like this. So we want to return two references, two mutable references. We need to check that the midpoint is in the right location, and then we can just return those two references. And just as an aside, it's worth noting that this assert is not like a C++ assert. This assert will fire in release builds. So this code, you know, will be correct. But if you try and do that, you'll get an error. And that's because you're trying to return two mutable references and the borrow checker can't tell that these don't overlap. So as far as it's concerned, you've taken two mutable references to the same object. But since we know as programmers that those references don't overlap and they are safe to manipulate, we can do it instead in an unsafe block using unsafe code, which under the hood will be using raw pointers. So here we're saying, okay, get the length of our slice, get a pointer to it. We're going to check the same condition that we were before. And now we're going to use this slice from raw parts mutable to get our two mutable references. And the calling code doesn't know anything about this unsafe block, but it's necessary to make this code work. Now, why is from raw parts mutable? Why is from raw parts mutable unsafe? Well, if you want to see that, you just have to look at the doc. So unsafe functions, if you do look at them in the code base, you'll see they have very, very long doc comments. So if you've got Rust on your machine, you can dig into any of these functions just by going to their definition, and you can look at these big comments. You can look at their implementation. You can just see how they work. So this from raw parts, which is what's called by from raw parts mutable, this is the unsafe line. This is dereferencing a raw pointer. And then it's got a little comment saying the caller must uphold the safety contract for from raw parts. But it's the dereferencing that makes it unsafe. Now, if we dig into the doc, you can see it says what it does. It forms a slice from a pointer and a length. And the length argument is the number of elements, not the number of bytes. And it tries to describe the safety conditions which are required by this function. So because this function is marked unsafe, it means the calling code needs to confirm something. And this comment tells you what it needs to make sure is not violated. So It tells you that data needs to be valid, tells you that the bytes need to be properly aligned. So the entire range of the memory of the slice must be contained within a single allocated object. The slices can't span across multiple allocated objects, and actually it gives you an example of that later. The data can't be null and aligned even for zero-length slices. It gives you an explanation of why. It's got another condition, which is that the data must point to the length of consecutive properly initialized values of type T, so they all have to be the same type. The memory referenced must not be mutated for the duration of the lifetime, except inside an unsafe cell. And the total size of the slice must be no larger than I size max. And if you want to see why, you can have a look at the pointer offset for why that might cause you issues if it violated that. Also gives you a caveat, so it gives you the lifetime, a little bit of information about the lifetime. And it also gives you an example of what might look correct, but would violate the preconditions. So the reason why it's in an unsafe block is because you could write this code and this code would be wrong. So here, what it's saying is we've got two allocated objects. They're next to each other in memory. But if we try to join those slices, then you're going to end up basically going across two type boundaries. So it's basically utter nonsense. But even though we've checked everything, so we've checked that the slices are contiguous, we haven't actually been able to check whether or not they're in the same allocated object. So it's undefined behavior. Might work, might not. Who knows what it does? But in any case, it should not be written. So that's kind of showing you kind of how you can dig into the doc of some of the unsafe functions if you want to know a bit more. Another example of unsafe code is using extern functions to call external code. So this is how you call out from one language into another language. In this example, we're saying, okay, you want to use a CABI for this function. And that means in an unsafe block, we can call that extern function, and it's actually going to call into our C function for the absolute value here. It doesn't go into a huge amount of detail of how to do this, but if you're interested, there is a lot of documentation over it, in particular with working with C APIs. But I also thought it'd be nice to put in some examples of Python ones, because I know there's a really nice doc on it. So there's a Rust binding for Python interpreter called Pyo3, which someone called Mara Boss has used to create inline Python crate, which allows you to just write your Python inline in your Rust code, which is really handy. And then there's also a compile time Python crate, which means that you could say, for example, you wanted to write an application where you wanted to read from a file at compile time, load it up somewhere, and then do something with it. You can do that at compile time by running your Python code within your Rust code, and then when your Rust application is running, it doesn't need to run that Python code again because it's already done it. So there's some nice uses, but they all underlying rely on that extern API. They'll have a C API that they use to call into Python and to get those values back out, which would be totally impossible to check the correctness of using the borrow checker and using the various other safety checks that Rust has. But if you put it in an unsafe block, you're saying, look, I will check. I will make sure this works. Mentioned earlier about the dreaded global. So that is another example where you need to use unsafe Rust. And by convention, if you've got a global, which is this static keyword, then you should write it in screaming state case, which I think is because they've obviously used globals in other languages and know how much trouble they can get you in. So if you want to access and modify a mutable static variable, then you have to use the unsafe keyword. And that's because you really get absolutely no safety guarantees with these. So if you've got any kind of threading going on, you get two things trying to modify it at once. It's very hard to reason when you have a lot of globals. So I think it's generally a good thing that you have to wrap it in an unsafe keyword. So yeah, it would likely result in data races if you had multiple threads accessing counter. But yeah, even without that, it's very hard to reason about complex code if you have a large number of globals in. So it's good to have those ones highlighted. There's also implementing of unsafe traits. The book doesn't go into a huge amount of detail here, and I probably won't either. The example they give is sync and send, which if you cast your mind back to the fearless concurrency, these are some of the traits that allow you to use types with multi-threaded code. So send means the type is safe to move from one thread to another. And sync means that it's safe to pass a reference to it from one thread to another. And the compiler can't actually verify the invariance of these traits. That's why the Rust language implements these traits for us on all of the standard types that can implement it. And then any composite types that we create will already be sync or send. They'll already implement sync or send by virtue of all of their parts implementing sync or send. But if you wanted to do it on your own type that was made up of a type which isn't sync or send, but you for some reason knew that you were able to satisfy the trait requirements because of the way you set it up, then you could implement an unsafe trait yourself. If you want to look at doing that, I would love to see it. I started having a look at it and I decided I never wanted to write my own implementation of sync or send unsafe trait, because it's quite difficult, I think, to reason about whether or not you are actually going to violate these conditions or not. The main example of where it doesn't would be, if you want to use a real pointer, it's not going to be sync or send. But if you know you're only going to be using it in contexts where it's allowed, then you could implement this trait yourself, but you would have to use the unsafe keyword. And the final example of an operation which is required to be done in an unsafe block is accessing the fields of a union. So if you haven't used unions in other languages, in the union in Rust and in C as well is similar to a struct, but only one of the declared fields is used in a particular instance at one time. So you just have one block of memory, but then it could be any one of the different types, depending on what you've chosen to put in there. This type in Rust is primarily used to interface with unions in C code. And as you can imagine, since that memory is the same memory, the accessing the union fields is unsafe, because Rust can't guarantee that the type of the data that you've said to access is actually the type that has been stored in it. So the example here is we've got a union using the data layout representation that C uses, and we've got two fields, F1 and F2, which are U32 and F32. If we put a 1 into there, we could still access it using F2, and it would just be essentially doing a reinterpret cast, which is why if ever you do want to access one of the fields, you have to put it in an unsafe block, because you have to say, look, I know that I put in an unsigned integer into this, so I want to use field 1. And then that way this will work, and your resulting F will be an unsigned 32-bit unsigned integer. So as mentioned, so unions don't have a notion of an active field, which means you don't know at this point, if you try and use U, there's nothing left in your union that tells you that only F1 is in use. Maybe you created it with F2 instead, and once you try and access the fields, there's absolutely no information to tell you that. Which means that every union access just reinterprets the bits using the type that you've said is in there. Which means you can use this for tricks, for doing any kind of bit twiddling tricks and stuff. Sometimes you'll see people will do it just to get a cheap and cheerful reinterpret cast, basically. So you can convert between the bit storage and modify it as one type, even though you know it's a different type. But crucially, it's the programmer's responsibility to make sure that when you access the data out of your union, it is valid for that field type that you said is in there. The reinterpret cast is kind of like C or C++ terminology, but in Rust it would be called transmuting it. And yeah, failing to do this correctly gives you undefined behavior. If you put in one type and you try and get out a different type, you don't know what you're going to get. So for example, the example they give is reading the value of 3, but saying this value of 3 is a Boolean. Well, I don't know how you convert 3 to a Boolean, but we'll have to wait and see. If you try and reinterpret those bits as a Boolean, then anything really could happen. But that's not to say that unsafe Rust code isn't safe. It very much can be safe, but it's just that it's the programmer's responsibility, which is the situation you're in with tons of other code already. And bugs may still happen, but the unsafe keyword makes it much easier to track them down when they do occur. Is there any chat or any questions at this point?
We have just had one question come in, actually. Just, are you aware of any converters between union and enum?
I think union, you might still be able to do. No, you can't. No, I can't. I don't think there are, because I'm not sure what that would necessarily look like, because there's no way of knowing what's in your union to then map it onto the enum values. So once you've got a union, you've lost any type information other than that it's probably one of these types. You know, it might have an unsigned 32-bit integer in it. It might have a 32-bit float in it. Once it's a union, you've lost that information. So you could write your own converter in an unsafe block, but you would have to know what was in it already. Yeah, but it gives you so much flexibility that I will plow on, because much to cover. Oh, sorry, Matt.
I just want to say one quick thing. There's a whole documentation on writing Unsafe Rust called the Rustonomicon, and I'll link it in the chat. But if you want to go into the realms of unsafe programming, read that first.
Yes. Yeah.
Excellent name.
It's a great book, and I think there'll probably be lots of scope for future talks in it as well, because there's a lot in it, and really gets you into the weeds. So the next section is advanced traits, or as I have decided to call it, trait secrets, because I think that's a lot more fun. And going to go through some of the kind of advanced capabilities of traits that are really useful in certain instances. Some are more useful than others. Some of them seem a bit esoteric, but they all have their place, even if we might never have to write them ourselves. So the one which you probably will come across and will use actively is placeholder types. Back in chapter 13, you might have tried to implement your own iterator as part of the kind of functional language chapter. It showed you that you can, and that you can create your own custom type, and then you can implement iterator on it. If you do that, you have to put a placeholder type on it, which is this type item. So when you create your iterator, you're saying, okay, I need to specify what this item type is. And that way, the next method, which is required for the iterator trait, will return an optional to that type. So yeah, the implementers of the iterator type will specify a specific concrete type for that item, and then they'll use that in the return value. And that's different to using generics. And there's a reason why we don't want to use generics. So the easiest way to see it is to actually try using generics. So if you put a T in there and said, okay, when I implement the iterator trait, I need to specify the type, and then put in the same, so function next, which then returns an optional to that T. But the reason that's a problem is that on any given type, you could implement iterator multiple times with a different value T, because it's a generic type. It's not actually linked to the underlying type. So what that would look like is you could say, okay, well, this is my iterator trait definition. If I then said, okay, create my struct iterable, and then I'm going to implement that trait, I need to say, okay, I'm using an unsigned 32-bit integer, and then I can call next, and it will return an option to that type. And in my case, I'm just returning something, but you would actually return the next value in your collection. But there's no reason you can't implement that trait a second time for float 32, which might be total nonsense on your type. Or it doesn't have to necessarily be total nonsense. It could be totally valid, and maybe you want to have an iterator that can have multiple return types on next. But that kind of violates what we want next to do. Usually if you call next on this object type, it's always going to return the same thing. So we just want to call next like this which if we just had one trait implementation of that generic iterator trait would be fine. But if we've got one for float and one for unsigned integer, then you end up having to write something like this, which is not the most aesthetic code in the world, and also not really what we want for next. We only want any given type to be able to implement next once. You don't want it to be able to implement next as many times as it wants, because it's not really how next is designed to be used. So that's why it's done using this placeholder type instead. So with a placeholder type, it will end up looking kind of, you'll only ever be able to have one implementation, which means it ends up looking simple all the time. Yeah, I didn't put an example of what it actually ends up looking like, but yeah, it's straightforward to implement if anyone wants to try. If you make your collection a bit more complicated, then you do have to be careful with your lifetimes and things for implementing your own collection types, but it's very much doable. And then you can play around with implementing your iterator trait. So now we're on to the next advanced trait option, which is default generic type parameters, which is exactly as the name suggests, very straightforward. It's just using a default type when we're setting it up. So here, our trait is a generic trait. It also happens to have a placeholder type, but this is not our placeholder type. This is our generic type, which is used here in our add method. So that if we know that when people are implementing add, the most common use case is for adding to yourself, like another instance of the same type, then rather than forcing every person who wants to implement add to specify that they are adding to themselves, you can say, okay, if you haven't specified the generic parameter here, then I know that you're adding to the same type, which is just a nice, convenient way of avoiding having to write additional code if you know you're not going to use it most of the time. So in the example of taking a point and then adding 2 points together, our output's a point, but that is separate to the generic parameter, which is this one here. But we haven't had to specify the generic parameter because it's defaulted to self, which means it's defaulted to point as well. So we just write it as normal. And then we can say, okay, when we're adding 2 points, we want to return a point, and this is what that looks like. So it's nice and simple. And that's instead of needing an extra type parameter here, which can look a bit confusing. There are two main reasons that you would do this. So I've kind of mentioned one already, which is if most users are just going to be adding point to a point, then there's no point using, sorry, misuse of the word point, but yeah, there's no point using an extra, forcing them to specify an extra type when you're always going to be adding a point and a point. But sometimes you might want to add, for example, a point or a line to a point, for example. So I've got a line and then I want to add another point to my line. Well, then I might want to be able to add a line to a line, but I also want to be able to add a line to a point. And in that case, it would return another line. You can also do it to extend a type without breaking existing code. So if you've never had a generic parameter on it, then you can't just add one in, because if you add one in, you're going to break all of the existing codes. So by defaulting that generic type parameter, you can get around that and extend your API without breaking a load of other people's code. The next section is, so still in advanced traits, is when you have to use fully qualified syntax for disambiguation, i.e. calling methods with the same name. We've kind of already touched on this, but just to explain when you would use it. So there are only so many good names to go around. And if you're implementing a lot of traits, then you will find sometimes you get a name clash. So the example they give is flying. So if I want to implement wizard, I need to implement fly. If I want to implement pilot, I also need to implement fly, but maybe my human can already fly. So we've got a human that can fly, but it can also fly, but it can also fly. So when we call person fly, our person's a human, but which fly are we going to get? It's going to default to the method that's implemented directly on the type, if there is one. If there isn't one directly on the type, then it won't be clear which one you're using. And if there is one on the type, but you want to access a different one, then you have to use more explicit syntax. So that ends up looking like this. So we say, okay, on the pilot type, I want to call fly, and I'm going to take a reference to myself, which is person. And that way it'll behave just as if we'd called fly on it as normal. But that syntax only worked because our method took the self parameter. If it didn't take that, then we couldn't call this, because pilot fly with open brackets, close brackets has absolutely no reference to our type, our underlying type, which is human. So how do we know? How do we know what on earth it's doing? So, for example, if we take a dog type, so we've got our struct and saying, okay, a dog has a name, but a dog is also a baby animal, and baby animals have special names for baby animals. So we say, okay, let's implement baby animal for dog, and whenever we have a dog, the baby animal name is puppy. So name, we're going to get dog name. So how do we get baby animal name? We can't do something like this because it doesn't take a self parameter. Our name method didn't take any parameters. And we can't do this because that just prints spot. And we can't do baby animal name because that could be any animal. You know, it could be a baby cat, and that would return kitten. So how do we call this? Well, we're going to end up using the same syntax that we saw earlier with our iterator if we tried to define our iterator trait using generic parameter type instead of the placeholder type. So here we've said, okay, a baby dog is called, we take our dog, then we get it as a baby animal, and then we can call name on it. And this way we've added this type annotation to know which name function we're supposed to be calling. So just to remind you, this was what the iterator type looked. A float 32, for example, and then we called next on. In that case, it did take the self parameter, but it was on the same type, so it didn't help us anyway. Yeah, so that's the fully qualified syntax. This is the worst it should get. Obviously, your types within it can get quite long, but it's nice to know you can call that when you do have that ambiguity. Now moving on to advanced traits using super traits, which is using one trait and requiring another trait so that you can access all of the methods on it without having to use concrete types. So for example, if we have a trait heartprint, then we might require implementing display so that we can call to string, which we know if anything implements the display trait, then we can call to string on it. And so if it implements display, we can say, okay, I want you to also implement heartprint, and we don't need to add anything else because it will just work. And we can also have multiple requirements. So we can require, for example, our heartprint to not only implement display, but also implement lovable. So on our type programming, we can say it needs to implement the display trait for programming. We write our little implementation for that. And then we also need to implement lovable for programming, which is just an empty trait, but we still need to implement it. And because we've done that, that means we've satisfied both of the conditions that were specified in our trait definition. So now we can implement heartprint for programming, and without having to do anything else, we're now able to call this heartprint method. So that's kind of the super traits are pretty straightforward. They do what they say on the box, and they work pretty well. They're very flexible. The next section is new type pattern, which is to implement external traits on external types. In this case, anyway, new type pattern we'll also see later in another context. But we can only implement a trait on a type if we either own the type or the trait. So we have to have local to our crate has to be the definition of either the type or the trait, which means you can't take a trait in some crate that you've pulled down from crates.io and some type that you've pulled down from another crate or from the standard library and then implement that trait on that type. It just won't let you. And the reason it won't let you is because you could then have clashing definitions for the same trait. So you could have someone else could have implemented this trait as well on this type. And then when you pull in another crate, you've now got two conflicting trait implementations for this other type. Whereas if you always own either the trait or the type, then you know that there's only ever going to be one attempt to implement the trait for that particular type. But the downside to that is that we then can't implement traits we don't own on types we don't own. So we can't, for example, implement format on a vector of strings. To get around that, we use the new type pattern. So we basically put a thin tuple struct wrapper on our underlying type. So here we've got my wrapper, vector of strings. And now, because we own the my wrapper type, we can implement it. So we can implement format display, even though we don't own this trait and we don't own this type, we do own the wrapper type. So we can now implement it. It's a little bit uglier because you now have to access the underlying type if you want to use any of the methods on it. So for example, on vector of strings, I can call join, but I can't do that on my wrapper. So I have to get the vector of strings out in order to call join. So that's what I was just mentioning there. But then once you've got access to the inner type, you can do all of the same normal things. So I've got my wrapper type and I can access the element inside and call sort, for example. If you really wanted the new type that you created to have all of the methods of the inner type without having to do this .0 every time, then you could actually implement the deref trait, which we saw in an earlier chapter, and you can implement that on your own custom type. And that way it would implicitly do that resolution for you so that you could call sort on your object of my wrapper type, and it would be able to access the vector method for sort, and it would just do the job for you. Whew, that's the end of advanced traits. So does anyone have any questions at that point, or should I just plow on with advanced types, or any kind of comments or anything people thought about it? It's quite a good chapter, covers some interesting things, I think.
We've not had anything in the chat just yet, but feel free to unmute yourself, guys, and ask questions if you've got them. Or
all
just
right,
one comment. So far, very interesting.
I think Alex has just dropped out. Can everyone else still hear me okay?
Oh, no.
I think it's not my internet.
I can still hear you.
I can hear you.
Oh. You're back, Alex. You dropped out there for a second.
Oh dear. I'm all good now.
Yeah, all good. Right, I will plow on with advanced types in that case. So we're going to see another use of the new type pattern, but this time, rather than doing it in order to implement a trait, we're going to use it for type safety and abstraction. So this means we can create new types for known types, so that we can add a bit of extra information to what they are and really shore up our types. And in this case, we're saying, okay, we've got millimeters and meters. The underlying type we want to use is just an unsigned 32-bit integer. But when we interact with it, we want to treat it as either millimeters or meters. And that way you can do things like implementing add. If you try to add two unsigned 32-bit integers, there is absolutely no logic in there to force you to add them correctly if they're not the same. So in this case, we've said, this is how many millimeters we have, this is how many meters we have. If I add those two numbers together, I'm going to be treating them as if they're the same magnitude, but they're not. So by creating these new types, millimeters and meters, we can implement our own function, our own add function for an add trait. And that way, when we add them, it's a lot easier to tell what we're doing. So we're saying, okay, I want to take my millimeters, and then I want to add together the number of millimeters plus the number of meters times 1,000, and that way I get the result back in millimeters. And it's nice and clear what we're dealing with. It's very hard to get wrong if you've implemented it this way. And it also allows us to do things like expose a public API that's different to the API of the private inner type without re-implementing a hash map from scratch for our own personal use. We can just put a hash map in, wrap it, and then expose a different API. So for example, if we've created a a new type called people, which just contains a hash map of an integer and a string, we could then say, okay, when you add a new person, behind the scenes is going to generate a GUID for that person's particular ID. But the caller of this API never needs to see that GUID. They never need to know it exists. But we internally can still store it. So even though we're storing a hash map, we don't have to expose that to the calling code. And this is what that would look like. So you've got your simple tuple struct, which just contains a hash map. We've implemented new so that we can easily create one without showing them the inner type. And then we've said, okay, add person, this API is just take a self, take the string, and then insert it. But we'll call a new ID method internally to generate that GUID, which is a really lightweight encapsulation that's very, very easy to do. And that's something that you'll see a lot in terms of why you might use the new type pattern. Brings us on to the next section, creating type synonyms with type aliases. So this is different to what we've just seen there with the new type pattern, because we're not creating a new type here. We're just using an alias. So this doesn't give us any of those safety concerns like we got with millimeters and meters. You can still add, if you've written type kilometers is an I32, and you also wrote type meters equals I32, you could add together kilometers and meters and it wouldn't complain, even though you've got the scale wrong. But it would maybe be a bit easier to see what you've done wrong. So it can still be useful in certain cases, but it definitely doesn't give you the protection of the new type pattern. But it can still be useful though for like, if you do just want basically a type alias, you don't want any of that safety stuff because you're never doing anything special. So for example, if we're dealing with a type that's got a really long type description and we know it's going to be this, we're going to use it a lot, then we can just set up a little type alias at the top, and that way we can use it wherever we would have put in that long type, which can make our code a lot clearer. All right, another advanced type, and this is probably the oddest section, I would say, or the one that's like a bit head scratchy when you first read it, which is the never type. And the never type never returns. So my first thought when I read this was, what? Why? What on earth are you talking about? But it does have its uses. So these are the return type of diverging functions, which are functions which never return. And the way we denote that type is the exclamation mark. And what's useful about the never type is it can be coerced into any type because it never returns anyway. So the assignment is never going to happen. So here we said, okay, let X, which is our never type, equal panic. Well, this never happens. This never happens because panic never returns. So the return type of panic is our never type. The reason this exists is because there are cases where we don't have the concrete type to return. So the example given in Rust by example is this sum odd numbers function. We're saying, okay, I'm going to do this loop. Then I've got my match statement. And it's this one that's important. So if our integer is an odd number, then we're going to return I. And we're going to put that into our addition. But if it's false, we're going to continue. But continue isn't an unsigned 32-bit integer. So that this wouldn't make sense because continue does not return a 32-bit integer. But what continue does return is the never type, and the never type can be coerced into any type. And that way, all of the type checking that the compiler does, it all still works because this never type can be coerced into any type, but it never returns anyway. So you don't have to think, well, what happens if you assign a never type into an unsigned 32-bit integer? It never happens because the never type is never returned. it's a trick. It's a lie, but it's very useful. So continue is returning our never type. So the type checker is not complaining, and the U32 is you're only ever assigning an unsigned 32-bit integers into our addition variable. And this is also the return type of functions that loop forever. So our loop, if we just have a loop with just doing some work in it and just looping forever, like in a server, for example, then that loop is actually returning a never type, but the never type never returns. So it doesn't really matter that it returns a never type, but it does. If you put a break statement in your loop, then it no longer returns a never type. It returns a void if you're just breaking, or it returns whatever specific type you've put as returning after your break statement. And the other things that return never types are exit and panic. So though this be madness, yet there's method in it. So don't be scared. It's you'll probably never have to think about it beyond knowing that it exists. From what I've heard, I can't think why you would ever need to deal with the never type yourself, but it's good to know it exists, and it gives you a little peek behind the curtain of how internally the type checker and the void checker and all of that, how they manage to string together so nicely.
I use the never type all the time. Normally with the winit crate.
Oh, okay.
Start a window, because the event loop returns a never type. It never returns when you start running the event loop.
So, but you're still explicitly having to use it. Yeah.
Well, if I want to put that in a function, I can have a function return a never type, because any function that contains the call to run on the event loop will never return.
Interesting.
So
okay.
that includes the main. You put it directly in the main as well. So if you put like an OK at the end of the main function that returns result, it will come up with a warning saying that this code will never get called.
So there you go. Folks, you will get to use the never type.
I might offer to write some code in front of people using winit.
Yeah.
Image and pixels, and do it like so people could write an image view or something really quickly.
That would be super useful, because it's not something that I've interacted with. So when I was reading this chapter, I was like, this is very odd. But but yeah, the event loops are exactly the use case for it. So that totally makes sense. On to the next advanced type, which is dynamically sized types and the size traits. So this is something we've all interacted with, perhaps without using it so much. But yeah, so in this example, we said, okay, let hello equal, and then string literal hello. And the first thing to think about is, well, where is this actually getting stored? Is it the stack? Is it the heap? Is it somewhere else? I'm sure many of you know, but the first way to start thinking about it, if you don't already know, is, well, what type is it? Well, if we add a type annotation of str, it will error, because that is not what type this hello string literal is. It's a string ref. It's not a string. And the reason that we don't have it as string as just a straight string slice type is that it can't be, an str type, a str type, is that it can't be known, size can't be known at compile time. So we could have written hello world, we could have written hello and said that they were all str. But if they were all str, then they would also all have different sizes. So we couldn't just assign that on the stack with the way the Rust type system works, because we don't know its size of the str type. We know the size of the string, but not the str type. So that's because str is a dynamically sized type. So the correct annotation is a ref str or a string slice, which looks like this. So we said let hello ref string equal hello. And where that is stored is in the read-only data of your application. So it's not allocating on the heap. It's not being stored on the stack. It is allocating the word hello onto the read-only data of your application. And then the stack component is just a pointer to its address and its size. So that's one of the main ways that you'll interact with dynamically sized types, is that the stack object for it will just be the address and its size. And then you will then look at the read-only data on the application's executable, and there will be the data. And the error we got when we did that was mentioning that the sized trait is not being implemented. And the size trait is automatically implemented for all types where the size of that particular type is known at compile time. Which all there is, that's all I've put in to say about here. But if dynamically sized types is again you can go into a lot of detail in terms of writing your own and looking at other implementations beyond just a string type, but that gives you a nice idea of kind of the simplest example of string. And we will come back to it a little bit. But now we're going to move on to advanced functions and closures, which are not as scary as the title sounds. It's actually fairly straightforward if you've looked at function pointers in the past. So let's talk about function pointers. So function pointers allow us to pass functions to other functions, as opposed to closures, which we looked at in the functional chapter. And these, because closures are anonymous and they might capture state, and they're slightly different.
Can I quickly say something about sized?
Yeah.
What's not obvious is that size is assumed whenever you use generics as well. So if you use like I want T to be based on foo, it really does mean foo plus sized. That is always applied. If you don't want it to be sized, you have to opt out of it using exclamation sized. And if you don't care, then you need to do question mark sized, which is maybe sized. And that looks a bit odd when you first come across it until you realize that sized is always assumed.
Yes, that's a very good point. Yeah, I probably should have mentioned that. Yeah. If anyone wants to dig into that a bit more detail, we can maybe at the end kind of pull up the doc for it, just show people what that syntax looks like, because it does look a bit strange, but as you say, size type is automatically implemented for all the types of the size and compile time. So you'll only start running into those things if you're dealing with it.
Not just automatically implemented, but automatically declared in a generic. So if you do like type plus type, it just assumes a plus size in there assumed as well.
Yeah. Sorry, I meant if you're writing your own types, it will be sized. it will be sized, even if you're passing a string, because the ref string itself is sized. It's just the underlying type that's not.
It's a very special case in language.
Yeah, but it is useful to know about, because it does you will see it in code as soon as you start digging into some of the implementations for things. So on to advanced functions and closures. So as I mentioned, function pointers allow us to pass functions to other functions. That means in this example here, we're saying I've got a function add one, and I want to have a different function which takes a function and does that function twice. So we're saying I want to add 1 to 5, but I want to do it twice. And then that way you can get 7. And the syntax just looks like this. And this is different to what we saw in the closures example for passing around that, because that was using generic types. And the reason it was using generic types is because we didn't have a concrete function type. In this case, we have a concrete function type. It's the function that takes an I32 and returns an I32, and that is our concrete type. Whereas if we look at closures, you'll see we need to have a generic type which implements the function trait, or at least the function once trait. But here we're using the concrete type of function pointer, so it doesn't have to be generic. But you won't normally write this. And the reason you won't normally write this is because it's very rare that you would want to write a function which can only take a function pointer. You probably want to write something that can take either a function pointer or a closure. And function pointers will automatically implement all 3 of the closure traits, which were function, mutable function, function once, which are the ones you could only use just the once. And it's usually, as I mentioned, preferred to use the generic type parameters, and that way you can pass them both in. So just to compare what those 2 syntax look like, in this example, so we've got a list of numbers, and then we're saying, okay, I want to iterate over it and then map them onto strings and collect them. In this example, we're taking a closure, which takes our integer and then does to string on it. Whereas in this example, we're taking a function pointer to our concrete to string method. Our map function will have been implemented using that generic type, which implements the trait function once, and then that way it can take both of them. Sorry, not function once. It would have had to have been function, yeah. So that's kind of the only difference in terms of calling code of what it ends up looking like. And similarly, they choose to mention this, I think, because it's probably looks a bit weird if you don't realize what an enum is in the context of Rust. But they mention it in the book, so I thought I would mention it as well, which is that this is a function pointer. Might not look like a function pointer, it might look like a concrete, enum type, but this is a function pointer which takes an unsigned 32-bit integers. So that way you can map this list of 32-bit integers onto a collection of status which have that value in using this function. And if we wanted to implement it as a closure instead, it maybe would look something like this, but they both do it's the exact same thing. And what's slightly different about function pointers compared to closures is that you can actually return these, because they're a concrete type. We know how much size they take up, those function pointer types. They can actually be returned. Again, you won't see this very often. Someone correct me if they see it a lot, but you can write this. This will compile. But you can't do that for a closure. So you can't write something like this. Because it doesn't know the amount of space that takes up at compile time. So instead, you end up with something like this. The compiler error will lean you towards something like this, which is fine for simple cases, but for more generic return values, you end up wrapping it in your box type, and that tends to be, I would say, more common. This is something that we saw in the object-oriented programming section as well, I believe. And macros. So we've judged that very well because it's exactly 7:30. We're not going to cover macros this session because we don't have time and there's a lot to go into. And Chris would like to do a more in-depth session on it. So this one is a to be continued section. There's a ton to say. It's super useful. Macros are incredibly powerful in Rust and very, very useful. And we've already used them several times in terms of when you create your own vector, when you create when you call panic, when you print, all of those things are types of macros, and there are tons of other ones as well. So we'll look forward to that at the next session. But now I guess we're kind of open for chat because I feel like there's lots of scope for chat in this chapter now. So yeah. And the chat.
I think that's why everybody is silent, isn't it?
It's a lot. There's a lot in that chapter. There's a lot of cool stuff, and there's a lot of scope for going into more depths as well. Like that's, I covered what's in the book plus like a tiny bit more, but there's so much detail you can go into with each of these sections. I think there's a lot of scope, but it's kind of a springboard where it builds up that familiarity with all of these concepts so that when you see it out in the wild, you can be less afraid of it.
I didn't know about putting enums on function interfaces, because I've seen code like that, and it just felt like black magic. And I wondered what the actual Rust rules that allow that to happen, and this would have been it.
Yeah, I think that's why they put it in there, because it's not like you need to write it. You can get by without it. But if you saw it, you'd be like, what? What is this? Why is this? How does this work? But yeah, you're essentially just constructing that enum instance.
Those
So,
are constructors, right?
yeah, it's just a constructor, but it just looks weird because we're so ingrained of what enums are with other languages that it's slightly different with Rust. So a bit of a sidestep.
So, Ciara, when do you think we'll have our next meetup?
Well, Chris would be the one to ask about that, because macros is the next, is what would be really nice to cover.
Of course. Chris, are you still with us?
I know Chris is a bit busy at the minute, but if he can't cover it, like I'll steal it from him because macros really interesting if anyone else wants to. It's yeah.
Obviously, it's the part which we can split for for this part of procedural macros and declarative ones. And there is possibly coming also new version of declarative one.
I just found out. I just only found out yesterday that the macro rules works in the same crate that you use it. Can use it, whereas normally when you define macros, it has to be in a separate crate. Didn't realize that.
Ah.
Can you repeat that, please?
So usually when you're using the macros in your code, like calling a function with the exclamation mark syntax, that macro has to be defined in a separate crate because the crate has to be built first and used during compilation. But I've seen, I hope I haven't got this wrong, but I've seen code where there's another way of defining macros called, I forget what they're called now. There's a macro you can use to define macros. Is it just called define macros or macro underscore define or something? Macro rules. There's a macro rules macro, which is kind of like a sub language within Rust to declare very simple macro functions, kind of like hash define in C, but a bit more powerful than that. You can define though. You can use the macro rules declaration in the same crate that you actually use the macro rules. So if you're doing a lot of code duplication and you want to repeat it, you can use macro rules and then define it at the top and then use it straight after underneath it. You can't do that with normal macros.
And that's the crucial bit, I guess. You do have to define it at the top. So if you've gotten used to writing regular Rust code where you can just shove things wherever you want and it all just works with macros, you do have to define it first because it's meta programming.
Yes, I think,
so it reads down the file.
Mm-hmm.
It is, yeah. But people from the C++ world will be used to that, so it's yeah, not so painful.
Yeah, it could be quite a lot of fun with this one.
Yeah, everyone can bring their own macro. Bring your own macro to the session. And show us what you've written.
Rust macros are pretty cool, but not quite as cool as Lisp macros, unfortunately, but close.
Oh, you might be the only Lisp programmer in the house today. Not sure. Any other Lisp programmers?
Well, the advantage of Lisp has is that data and code is exactly the same representation, and so you can treat data as code and code as data, and that gives you a lot of power with macros. Rust is more like a plug-in into the parser.
Yeah, it's like a first pass. It's like a
which is still more than C++ has.
But I think it still can, during the compilation, it can run as executable, right? Because that's why some of the SQL engines are like generating schemas, validating schemas.
Yeah, there's some really cool ones where you can do HTML exclamation mark and then put actual HTML stuff in there. Some web servers do that. It's pretty cool. So you have like a sub language. You can do some really cool stuff.
Well, like the Python compile time Python I mentioned earlier. So that's when you're compiling your code, you're running Python code, and then
that's insane.
And that raises security vulnerabilities issues, right?
It's not saying you should use it. I'm just saying
you
can.
I mean, so I've heard like the argument for C++ const eval that so some of the people were saying, oh, why we cannot just run something during compilation in const eval const expert, right? And some people said no, because that might execute something that you don't really want. And that's a security problem.
That's a really silly argument, mainly because it happens to compile time, and I can't forget it. Was it Dennis Ritchie or someone like him was talking about you can never ever trust your compiler because the compiler can insert code that you don't know about. So there's nothing that's secure.
This is less about trusting, not trusting the compiler, but it's more about using a third-party code that really might be vulnerable, right? So this is like recently there's been, and every now and then,
right,
npm, right, has some vulnerabilities that lots of the packages depend on the lots of the packages, and that's the same thing in Rust as well, right? You pull one dependency and that brings up some other dependencies as well, and so that's a the delivery chain attack, right? That if someone gets hold of the access to the crate, in this case, to the package in npm, right, that other packages are depending on, they can inject execution of something that potentially you don't want to, right?
That's true. That might be another great topic that we haven't. I don't know if you have covered in Rust Cardiff, is cargo plugins, because you can talk about cargo audit and cargo edit and lots of cargo plugins.
Yeah. But so those are having like CVEs that people have raised, right? But
yeah.
But
there's a research team as well, right? That actively go after and test things. But yeah, it is dangerous. It is risky.
Yeah, and you know, like with cargo, and I'm not like picking on cargo on Rust, right? But cargo repository, right? It is maintained by people who are like open source. So they have limited capabilities, basically, right? They're not being fully paid for maintaining everything, going through the dependencies and observing every package, right? So yeah, there is a potential for.
I have thought about, because I'm a lead at a company, and I've been thinking about this problem for using Rust within a company and trying to get people on board with Rust, and that the cargo crates thing, like npm, is a weakness. And I've been thinking about perhaps writing a tool where that can analyze all your crates, list all the authors, and you can go in and whitelist certain authors that you trust. And then it'll just show you the stuff that you don't trust, and then you can look into that and really audit it yourself and manually.
Mm-hmm. But that's
that'll be.
Is there a chance you trust an author, but still someone gets hold of access to his crates, right?
Well, if they go on.
Sorry. What you really want is like cargo. You want to be able to do your cargo build, but against your own internal crates.io. So, which I'm sure you could do, and then that way you could still access them from crates.io.
Not easily, and unfortunately, you have to. It's a command line that you have to override the default behavior, and that's one thing I actually would love to see in the Rust ecosystem, is a way of easily setting up your own server for your own crates.io. So and cargo would just automatically go there without any additional command lines, stuff. Because that'd be really good for like companies who want to take it on.
And then that way the vetting process then is, as the person who takes it from the official crates.io to your internal crates.io, that's the vetting process. And
cargo can use alternate registry. So from the cargo book, you can specify in the configuration, you can specify registries, and you can put
URL. But creating registry is not that easy. But you can also, of course, use specific version numbers when you're on your dependencies. So
that's correct. But I think there is still the potential for attack that someone overrides the version, right? So it's not
that's incredibly difficult.
Or like a force push if you're the owner of the repo. I don't think you can do that
crates.io, because I don't think publishing will work. Override.
All right, I didn't know that.
Unless they have access to a GitHub repository and change it into, that'd be very difficult. They would have to take over the GitHub repository.
But they might already be owners of it. That's the thing with the npm one, is it was the owner of the crate being like, nah, screw you.
Transferred, yeah.
So it was, and that.
But you can't do that.
Happen.
if a Rust developer says, "Screw you, I'm not sharing my code anymore," they can actually remove it.
They did keep sharing their code. That was the problem. They inserted the code where if you came from a specific IP address, it blatted over anything it had access to, and it did a ton of damage. And especially because people who are on VPN and they're not even from that. There's basically it was a protest in theory against the Russian invasion of Ukraine, but in reality, apparently deleted a load of data that was basically whistleblowers from Russia and Ukraine, kind of saying the things that had gone on. And this, obviously the organization running the code should have had better procedures in place, but equally, crate owners should not, or the package owners should not have just done this and not thought about the consequences. But
there was an NPM case where one program just says, "Screw you, I'm removing my packages from NPM completely." It was a left pad, I can't remember.
I think so,
but like everything was shut down, right? But you can't do that with crates. When you publish something, it's there forever. You can't remove it. Yeah. So be careful.
I would be interested to know if force push still works though if you own the repository. Can you?
No, because it will get from a particular. It would get from a particular
commit ID.
Commit ID, yeah.
But if you force push,
SHA-1.
Although I guess even if you force push, it should still have a fresh ID. But you could.
It will have. If it's different, it'll have different ID.
I know SHA-1. Yeah. Like for example, you should never. Yeah.
You're already thinking of hacking crates.io now. I can see the dangerous thoughts in your head.
How you can keep it safe is I actually have to shoot on as well, but looking forward to the chat on macros.
Oh, it's Ken Thompson. Thank you. Yeah, reflection on trusting trust. Yeah, I use one of those guys.
If you guys want to keep talking, that's great. I've just transferred ownership of the meeting over to you, Ciara, but I'm afraid I need to shoot off.
I always have to shoot off, unfortunately, but yeah, I would keep chatting, but I do have to go now. But see you all next time.
Thank you, Ciara. That was a great talk. Thank you very much.
Thank you.
Yeah,
thanks, Ciara.
Thank you very much.
Yeah.
See you all next time.
Have a good evening.
Good evening.
See you. Bye.